The next talk in our secure messaging session is on analyzing chat encryption in group messaging applications, and our speaker is Akshaya Kumar.
Everyone, I'm excited to share our analysis of analyzing, sorry, I'm excited to share our work on analyzing group chat encryption algorithms in messaging applications. This is joint work with Joseph Yeager and Igor Stepanovs. For a few years now, the cryptographic community has tried to provide the average user with end-to-end encrypted communication. To meet this need, end-to-end encrypted or secure messaging apps have seen massive success with deployment across various platforms that encrypt content under keys that are only accessible to the endpoints of the communication. Not just that, we as a community are also coming up with the messaging layer security standard that standardizes end-to-end encryption. Collectively, these apps are used by billions of people, so it's really important to study the real-world security of these applications. Our work focuses on group chat encryption algorithms in these apps. In the group setting, members of a group chat want to establish an encrypted channel with some help from a server. And broadly speaking, secure group messaging can be viewed as the composition of two building blocks. The first of these is key agreement, which establishes a shared symmetric key among group members. And this can be done in a variety of ways, depending on what security guarantees we want. This is considered the novel part of key agreement, of group messaging, and has received a lot of academic attention. And we don't focus on that part. Instead, we look at chat encryption, which is the second building block that actually uses the keys derived during key agreement. Now, what properties would we want from chat encryption? At the very least, we want privacy and integrity from an attacker that does not know the symmetric key. However, this allows group members to impersonate, and this can be achieved using secure symmetric encryption. But this allows group members to impersonate each other because all of them know the same symmetric key. And this is really bad because we saw in previous talks that protesters like to work in groups. And also, you might add an accidental outsider to your Houthi PC small group. And that way, achieving privacy is not really practical, but you still want that an outsider cannot impersonate group members. So normal privacy and integrity of symmetric encryption doesn't quite work in the group setting. We also want integrity against members in the group. In other words, we want chat encryption to guarantee sender authenticity against group insiders, as well as privacy and integrity against group outsiders. Naturally, we can achieve sender authenticity using digital signatures. This means that in addition to sharing a symmetric group key, group members additionally have their own signing key pair. And we formalize chat encryption in group messaging apps as the symmetric sign encryption primitive that aims to jointly capture the security goals of symmetric encryption and digital signatures. Across two papers, we introduced a formalism for symmetric sign encryption and defined security notions. Then we looked at various messaging applications, identified their core group chat encryption algorithm, and made it fit our model. Then we used our security definitions to either prove these algorithms secure or find attacks in our model. Whenever we found an attack, we checked if these attacks translate into real-world attacks against the protocol itself, and this required looking at the protocol beyond, details of the protocol beyond the chat encryption itself. When we were coming up with security notions for symmetric sign encryption, it made sense to think about security in terms of group insiders and group outsiders. An outsider is an attacker that uses the application and may compromise individual users' signing keys, but doesn't know the symmetric group key. On the other hand, an insider is part of the group itself and knows the symmetric group key, but does not know the signing keys of anyone but itself. And it's in this latter threat model that we found most of our interesting attacks. Since we said that we want chat encryption to jointly capture the notions of symmetric encryption and digital signatures, natural way for constructing these is by composing these two primitives in either the sign then encrypt or encrypt then sign fashion. A naive sign then encrypt would first sign the message using the sender's signing key. then encrypt the signature and the message under the symmetric group key, then the sender will broadcast the ciphertext to the rest of the group. Encrypt and sign is similar, except the order of operations is reversed. And this is actually what we saw in each of the applications that we analyzed. They used variants of either the sign then encrypt or encrypt then sign construction. And for this talk, I think I'll focus on the first one. Naive constructions are dangerous because they lead to what we call context switching attacks. And to see these, let's consider two group members who are both in groups 0 and 1. Let's say our user U sends a message by first signing it with their signing key and then encrypting under a group 0 symmetric key, then broadcasting the ciphertext to group 0. What a malicious insider can do is decrypt the ciphertext using the corresponding key, then re-encrypt it with group 1 symmetric key and broadcast this forged ciphertext to group 1, effectively impersonating U to group 1. The core issue here is that the same signature is being interpreted in two different contexts. We found variants of these attacks, of this attack in MLS in session, although there it allows an insider to replay messages in the same group. There are also attacks where the symmetric ciphertext can be interpreted in two different signing contexts. To prevent these context switching attacks, we additionally need to bind the signing and encryption components. And for this, we want to additionally sign what we call the group key identifier, which is a value that uniquely identifies the symmetric group key, and depending on the encryption scheme, also the nonce and the associated data. From the other direction, we want to additionally encrypt the sender identifier, which is a value that uniquely identifies the sender's signing key. With that background, we're ready to look at an overview of our analysis. We looked at 5 different messaging applications, and for each of them, we found different kinds of insider and outsider attacks. In MLS, we found insider replay and reordering attacks that resulted from the lack of context binding. In session, we found insider and outsider replays, as well as outsider forgeries, that also resulted from the lack of context binding. Although we didn't find any attacks in Keybase, its key reuse and key cycles made it really difficult for us to prove it's secure. In Signal, we identified the outsider forgery attack that was previously identified by Balbas, Collins, and Galland in 2023 that results from the use of a symmetric encryption scheme that does not provide integrity of ciphertexts. Finally, we did find attacks against Matrix in our model, but the way their algorithm was used in the broader protocol mitigated these attacks. That's a lot to talk about in 20 minutes, so I'll focus on the first 3, starting with MLS. MLF is the IETF standard for group messaging, standardized in RFC 9420, and has several implementations, including ones by Amazon and Cisco. MLS uses a really big data structure to derive encryption keys to ensure that each message sent in the group is encrypted using a fresh symmetric key. Members' public keys are used to derive the secret key. Then that key is used to derive a whole bunch of other keys. And then that key is used to derive another bunch of keys, eventually deriving the encryption keys. The encryption keys here are uniquely identified by what group you are in, where you are here, which is called the epoch, where you are in that tree, which is called the leaf index, and finally, where you are in that chain, which is called the generation. What you need to take away from this complicated looking picture is that every member in the group stores this big structure, and encryption keys are uniquely identified by this 4 tuple that we call the group key identifier. Now let's look at how encryption keys are actually used to encrypt chat messages. MLS composes an AED scheme, a signature scheme and an AED scheme in the signed and encrypt fashion. So first, it signs the message along with some metadata under the sender's signing key. Then it encrypts the message body and the signature under the keys from the previous slide using an AED scheme, and then the sender broadcasts the ciphertext to the group. Ideally, we want the signature to authenticate the key identifier of the encryption key so that an insider cannot re-encrypt the message with another key and replay it to the group. If we look at the group key identifier and what the signature authenticates, we see that the signature authenticates the group, the epoch, and the leaf index, but it does not authenticate the generation, which means that it does not entirely authenticate the group key identifier. This leads to attacks. If we look closely, the nonce is also not authenticated, and that leads to attacks with dubious values, so I will not discuss it here. However, not authenticating the generation leads to attacks because it allows an insider to move between generations here. And in practice, what this allows an attacker to do is replay and reorder messages. And I'll lay out in detail the replay attack for us. So let's picture this group chat where our user asks this benign-looking question. Our honest member responds by saying yes. They first sign this message using their signing key, then encrypt the signature and the message under this encryption key, and broadcasts the ciphertext to the group. Let's say that the identifier for the encryption key is this for tuple. When members decrypt this ciphertext, their clients will display this message. What a malicious insider can do is leverage the fact that the signature doesn't authenticate the generation by using this decrypt then re-encrypt technique that we discussed before. So first, they would decrypt this message, the ciphertext using the corresponding key, then re-encrypt it with a different symmetric key that has the same identifier, except the generation 1 here is the future generation. And they save this forged ciphertext. Then they send a potentially incriminating question in the group chat and impersonate our honest member by forwarding the forged ciphertext to the group. To other members, it appears as though the original sender resent their message. MLS aims to specifically prevent insider attacks, where the attacker knows encryption keys, but should not be able to send messages as though they came from someone else. And the lack of authentication of the generation violates this very goal. We saw that the attack resulted from the lack of binding between the signature and the generation, so the fix is to bind them. MLS already signs the associated data, so an easy way to achieve this is by including the generation in the associated data, while still being compliant with the specification. However, this leaks the generation, since the associated data is sent in plain and could lead to some privacy risks. We disclosed our findings to MLS, the working group, by posting to the mailing list. The turnaround time was really quick. Highly recommend contacting the mailing list. They acknowledged our findings and invited us to present at last week's ITF 1-2 meeting. And since then, a PR has been approved that modifies the architecture document by disclaiming that MLS doesn't prevent insider attack. And this modification also suggests application layer fixes. Future versions of MLS are likely to fix it at the MLS layer by achieving this binding between the generation and the signature. We also found insider and outsider replay attacks in Session, which is a privacy-focused decentralized messaging application with about 1 million users, and it offers end-to-end encrypted group chats for groups with less than 100 members. We found insider replay attacks in Session, which, morally speaking, were the same as the attacks in MLS. And this resulted from the lack of binding between the signature and the group key identifier. This made us think about replays in general, and we found that Session doesn't cryptographically prevent replays in general. This is because every ciphertext that is sent in Session is accompanied by a timestamp, and receivers use this timestamp to detect replays. This timestamp is not authenticated. This allows anyone, including a group outsider, to simply modify the timestamp and forward a replay ciphertext to the group. Of course, an outsider doesn't know what message they're replaying when they're executing this attack, so a non-insider may find it difficult to extract value from this attack. When we disclosed our findings to Session, they acknowledged this attack and also corrected our understanding of some other attacks, but it turns out that they were already developing this new version for group chat encryption that they called Groups v2, that soon after replaced the legacy groups protocol that we analyzed, that is supposed to fix most of the important attacks that we found, though we've not formally analyzed Groups v2. I would like to conclude on a positive note by discussing Keybase, where we didn't actually find any attacks. Historically, this was the first of our analysis, and the explicit use of an algorithm that combines symmetric encryption in signatures in Keybase is what motivated this line of work. Keybase is a suite of encryption tools, including a public key directory, an instant messenger, and cloud storage. It has about 1 million users. we analyzed Keybase's group chat encryption algorithm. In Keybase, members of a group establish a shared symmetric key. Thereafter, every message sent on the group is encrypted using this key. To encrypt chat messages, Keybase uses an encrypt, then sign, then encrypt construction, where it first encrypts the message body under the symmetric group key to produce the body ciphertext. Then it combines the hash of the body ciphertext with the sender and group key identifiers and the symmetric encryption key itself to produce the message header. This message header is signed under the sender signing key to produce a signature. To hide the signature itself, the message header and the signature are then encrypted using the symmetric group key to produce the header ciphertext. The sender will then broadcast the header ciphertext and the body ciphertext to the group. Previously, we said that we want the signature to authenticate the group key identifier, which is true in the case of Keybase, and that makes us really happy. However, Keybase additionally signs the encryption key itself, and that means that the signature is derived from the encryption key. Ultimately, the message being encrypted is derived from the key used for encryption, which is commonly known in literature as key-dependent messages. Generally, traditional symmetric encryption guarantees don't hold under the presence of key-dependent messages, and that makes us sad. To account for this, we had to show that the encryption scheme used in Keybase is secure under key-dependent messages that are derived in this specific way. And for that, we leveraged the observation that the signing algorithm here hashes the message before signing it. Then we showed in the random oracle model that the encryption scheme used in Keybase is secure under messages derived from a hashed key. This still doesn't make us happy because it wasn't easy to do. Another thing here is the same key is used in two different contexts. And we know from our first talk that this is a bad thing, and we want to prevent potential forgeries that allows an attacker to take a ciphertext from one context, move it to the other, and have it interpreted correctly. Once again, as we saw in the first talk, reusing keys across two contexts is okay if we have context separation, which can be achieved, for example, by prefixing the input of one context with a fixed string. Keybase did not implement explicit context separation, so we were sad once again. This should have led to an attack, but it did not. And that was because, on the one hand, the message body here is encoded using the message pack serialization format that leads to this body message always beginning with a fixed prefix. On the other hand, the input to the second context here always begins with a signature, which is highly unlikely to contain the prefix of the message body. We used a specific fact about the encoding scheme, along with the non-standard assumption that an attacker cannot find a signature that begins with the same prefix, to show that Keybase achieves implicit context separation, proving it secure. To wrap up, here are some key takeaways of our work, some of which are just retellings of folklore knowledge. First, sender authenticity is very important in group messaging apps, arguably even more than privacy. The second is that non-cryptographic encoding can oftentimes save the day, and we've seen this in previous analysis of Telegram as well. The third is that reusing keys across different contexts is bad, especially if there is no context separation. Combining encryption with MACs and signatures seems straightforward, but what we saw in our analysis was that their interactions can lead to subtle vulnerabilities. And the last is that formal definitions are important for real-world analysis because they inform secure designs that are simple constructions because we know what our goals are. And with the definitions in place, our attacks were in some senses easy to find. Details are in our papers. The second paper, with the grace of the ePrint editor, should be up soon, by the end of today, hopefully. Thank you.
Some messaging protocols try to provide a deniability property so that, for example, the signatures that you have in these protocols can't be used later as evidence against, say, an activist group. So it's obviously difficult to get all of those properties at the same time, but it doesn't seem impossible because if you had pairwise independent keys, then you could do it. So that raises the question, is it possible to do that in less than ON squared communication?
I'm sorry, if I understand your question, is it possible to provide deniability under symmetric sign encryption?
Yes.
Yes. So when we were designing the primitive itself, we were trying to model what happens in the real world. And most of the times it is that people are using regular digital signatures. And so it doesn't provide deniability, is why our primitive is what it is right now. But yes, it can be extended with something like ring signatures to make it deniable, depending on what notion of deniability one wants to achieve, which hasn't quite clearly been defined in group messaging, because deniability against the server or like offline, online, yeah. So
It's complicated.
there's definitely good work there.
Thank you.
Please join me in thanking our speaker again.